Hello and welcome to Lecture 6 of Math 2R03. In Lecture 6, we're going to be looking at Section 2.A of the textbook on linear independence. So basically, we're going to kind of finish up some of the material in today from that section. Last time we looked at the span, and today what we want to look at is linear independence. So like the span, this is a term you would have seen in Math 1B03, but now we're going to try to talk about what it means for a general vector space. So today's lecture, when we get kind of to the second and third part, we get kind of into the weeds, we get kind of some more complicated theorems, but I'll try to walk through them very slowly because they're kind of important for what we're doing. Okay, so first of all, let's just kind of remind ourselves, or if you're a little rusty, just kind of tell you what the definition of linear independent means. So a list of vectors in V1 through Vm is linearly independent if the only choice of coefficients inside of your field that satisfy A1 times V1 plus A2 times V2 up to AM times VM is equal to the zero vector is A1 equals A2, which is equal to AM equals 0. So the only kind of combination that allows you to make the zero vector is when all the coefficients are 0. A couple things to pay attention to is that sometimes we need to talk about the empty list, and the empty list is considered to be linearly independent. Okay, and then the opposite of being linearly independent is being linearly dependent. So a list of vectors that's not linearly independent is linearly dependent. And what that means, if we go to the definition, means that, i.e., there is a choice of non-zero AIs, or maybe I should say there is a non-trivial, there's the non-trivial choice of A1 up to AM such that A1 times V1 plus A2 times V2 up to AM times VM is equal to 0. So the non-trivial part is just saying that some of the numbers can be 0, but at least one of the numbers is non-zero. So these are the key terms here: linearly independent and linearly dependent. And let me give you some examples of these. So here we have the standard basis vectors in ALG3, and you should probably remember from Math 1B03 is that this is linearly independent. The only linear combination of these vectors that allow it to give you 0 is when all the coefficients are 0. If you take a single vector inside of your space, and if V is not the 0 vector, then V is linearly independent. So a single non-zero vector is linearly independent. What about two vectors? Well, if you take V and W inside of your vector space, we say that both of them are not 0. And if we know that V is not a scalar multiple of W for any C and F, then V and W are linearly independent. So what statement 3 is saying here is it's actually very easy to decide if two vectors are linearly independent or not. It's independent if one is not a scalar multiple of the other, provided we don't say that, provided that both of those vectors are not 0. And finally, in the vector space we introduced in the last lecture, right, which is all the polynomials of degree m or less, 1, z, z squared up to zm is linearly independent. Again, this is something that you may remember from Math 1B03. So here are some examples of linearly independence. What about an example of linear dependence? Okay. Well, here we have the following example. We have the vector 1, 0, 0, 1, 1, 0, and a, b, 0 in F3. And this is linearly dependent. And the reason is because if I take 1 times the vector a, b, 0, and then I take minus b of the second vector, and if I take b minus a times the last vector, and I crank this all out, what I'll get is the vector 0, 0, 0. Right? So the a and the b are allowed to be any numbers. So regardless of what the values of a and b are, I can find a linear combination that allows you to go to 0. And I get a non-trivial solution because I always have a 1 right here. So this gives you an example of something that's linearly dependent. And the following fact also gives you another infinite family of examples of vectors that are linearly dependent. If you take a collection of vectors v1 through vm, and if one of these vectors is 0, then v1 through vm is linearly dependent. Okay, and the proof is straightforward. We might as well just assume that v1 is the 0 vector, and then we notice that the 0 vector is equal to some constant times 0 plus 0 times the 0 vector plus 0 times the second vector plus 0 times the third vector up to 0 times the last vector. And this is a non-trivial solution for all non-zero coefficients inside of my field. Okay, so if 0 is in your set, it's automatically linearly dependent. So this is our quick review or introduction to linearly independent and dependence. In the next part, we're going to look at a kind of an extremely important lemma, which is called the linear dependence lemma.